Well, a warm welcome everyone to our webinar about drone simulations. Thank you all very much for joining us today. And once again, welcome to the Drone Simulation Zone. My name is Paul Lethbridge and I'm the Director of Product Marketing here at SimScale, and I will be your host today. Today's presenter is Steve Lanai. He is our Application Engineering Manager at SimScale. Steve has a degree in Mechanical Engineering and a PhD in Materials Science. Before joining SimScale, Steve worked in aerospace design and engineering simulation. So we are in very good hands today. A couple of housekeeping items if you're new to the webinar platform. First of all, please feel free to use the chat panel to introduce yourself, and also you can ask questions if you use the send question to staff option. And we'll go ahead and answer your questions during our Q&A session at the very end. Also, a quick reminder that your microphones will remain on mute during the presentation. With that, let's take a look at today's agenda. So it's a 30-minute webinar, and I'll start off with a brief introduction to SimScale and drone simulation applications. And then I'll hand over to Steve and we'll get into a demo of the drone simulation. And as I said, we'll wrap up with about a 5-minute Q&A session at the end, and also a little bit of information about how you can get started to try SimScale for yourself. So a quick introduction to the SimScale Cloud Native Simulation Solution. There's quite a bit of information on the slide here, but basically on the left-hand side, we have the traditional CAE situation where you've got to make a reasonable amount of investment in HPC hardware, quite a lot of high fixed costs, equipment costs, IT management, and also the tools typically have a fairly high barrier to entry. You've got to be pretty specialized to have training in order to use the CAE tools. Over on the right is the SimScale situation, which is, let's say, native cloud deployment of engineering simulation tools. There's no hardware required, basically zero hardware software footprint at your end on your premises because it's all in the cloud. It's very cost efficient, very cost effective. There's no fixed expenses, anything like that. You haven't got to have somebody constantly installing, updating, and so forth. And it's also incredibly easy to use, as you'll see in the demo. There's very nice collaboration tools. You can easily share your projects with your colleagues. Call to action, if you like, at the top is we really make simulation both technically and economically accessible and feasible. Why are drones important? Why? And we're probably all familiar with both commercial military drones, but also personal drones that people have. Probably seen them flying around if you're people taking photographs for real estate and so forth. I mean, basically, the market is huge. The drone market size is anticipated to reach over 500 billion over the next few years up to 2028. The compound annual growth rate is over 50%. I mean, it's a huge amount of market, large market growth. And this is all driven by both commercial and personal use demand. And there's a huge number of end use applications, as I'm sure you're aware. So SimScale is fundamentally a multiphysics platform, and it supports a very broad range of simulation physics that are applicable to drones and UAVs, as you can see on this slide here. So from CFD on the left, you can see use the tool to understand aerodynamic loads under varying flight conditions. You can look at, if you change the configuration of the drone, you can have a look at that, the effect on the payload, the endurance and the efficiency and so on. In the middle, you can use the tool to understand structural aspects of the drone, such as performing a drop test. You can look at the stresses on the drone blades, vibration analysis, and also in the electronics that are used in many of these more autonomous drones. You can understand the thermal effects of the right thermal effects, electronics. You can do a crush test on the battery pack and so on. Over on the right, a bit more info on the thermal is more around the electronics. So you can look at the electronics cooling. You can use the tool to understand the battery pack design to optimize that and validate that. Okay, so with that quick introduction, I'm going to hand over to Steve for the demonstration.
Thanks for the introduction, Paul. So let's get started on the demonstrations today. UAVs can be fixed wing, multi-rotor, or even hybrid. Today in this demo, we're going to be looking at a multi-rotor quadcopter. And we're going to be analysing the aerodynamic design characteristics and some of the structural aspects of this quadcopter to ensure a stable platform. So for the CFD, we're going to be looking at a hover case. Now, hover is one of the most important regimes for helicopters and multi-rotors. This is because at hover, it has the maximum power requirements. For UAVs and drones, the hover in ground effect, or in confined spaces, is especially important because they're designed to operate in close proximity to other things, to the ground or to buildings, and they're designed to take photographs within buildings or in confined spaces such as mines or even construction sites. And as well, more recently, drones are being used to deliver packages and small items, and that obviously means that they have to come to close proximity with the ground to deliver the package. Also, because they're often operated in urban environments, there are many obstacles that can be overhanging or shadowing the drone. And how a drone behaves close to the ground or these other obstacles is, of course, an important design consideration. The more insight we can gain into the physics that are at play, the better we can design for stability and for performance. So in the first part of this demonstration, we're going to look at the CFD side of things. So essentially here we've got a standard quadcopter, and we've removed some of the auxiliary items like the landing legs and the camera mount to simplify the CAD geometry slightly. And then in SimScale, we've created rotating zones. I'll show you that in the tool. And essentially, we've got a designer within your organization who's saying, what is the hover performance of this drone? What's the thrust augmentation due to the ground effect? And what are the rotor to rotor and rotor to airframe interactional effects? We've got various boundary conditions that we've set up to run this, but I'm going to show you that in the software itself. So let's jump to SimScale now. And we're looking at a transient simulation of this drone in hover. And we can see that there's no obstruction to the velocity coming out of the bottom of the drone. The drone itself is colored with a pressure map, so we can see the high pressure regions when the propellers pass over the airframe. But we can see that there's a nice flow of the downdraft from the propellers not being obstructed by any ground effects. So we can analyze the velocity that we've got here, but we could also obviously analyze the pressure as well, because that's very important so that we can understand how the pressure is affecting the airframe. So we could put a ISO volume on here to look at the pressure, and we can see that we've got some high pressure regions around the propellers, and the bottom of the drone itself doesn't have a high pressure buildup. So that's important to remember when we start looking at some of the other ground effect heights. So in order to run this simulation efficiently, we've actually done some mesh refinement in here. So I'll just show the mesh on here for a moment. So you can see the mesh refinement that was applied. I'll just switch off the drone coloring so that we can see that clearly here. So we can see that globally we have quite a coarse mesh, but around the areas of interest, so around the propellers, we've got a much more refined mesh. So this enables us to be very efficient, even with the large cloud simulation resources we've got available at SimScale. It's still important to be efficient so that we can run this sort of simulation in 200 minutes for a transient simulation. And in this actual simulation setup, we've run many different ground effect heights so that we can analyze the effect that the ground has on operation. So that was the transient analysis out of ground effect. For the steady state analysis, it actually only took 20 minutes to obtain a steady state analysis of the drone. So that's incredibly quick, and we could have run all these simulations in parallel to get all of those results back at once. So we've looked at the out of ground effect. Here's another shot of the pressure where we've got the scale up to 50 pascals here. You can see very little pressure on the underside of the airframe. Let's have a look now at maybe the H/R ratio of 2, so much closer to the ground. If we have a look at the geometry, we can see the drone very close to the ground here. And the results from this are that we have a much higher pressure underneath the airframe. So we can see a kind of balloon of a high pressure region above 60 pascals that is generated under the aircraft. Because as the drone is closer to the ground, more wake from the rotors is pushed outward and upward. And this wake creates this high pressure region. So it's important in the design process to make sure that the airframe can adequately withstand the loading while remaining stable. You can also see from the actual pressure plot underneath the drone that we have these high pressure regions on the airframe itself. So let's have a look how that's actually going. We can see the velocity coming down, causing this wake. And the other thing that can happen with this wake is we can also get some of that wake re-ingested into the propellers. So if we have a look at a particle trace here, we can see that some of the wake actually comes down and recirculates back up and is ingested into the propellers again. So these drones are often operated in dusty, maybe sandy, or even snowy environments. If we've got a situation where the wake is being re-ingested, it's going to circulate the debris from the ground up, and that could cause localized turbulence that could destabilize the aircraft, or even it could introduce foreign object debris into the motors or into the workings of the drone itself. So it's very important to understand how these effects can actually happen. So that's some of the post-processing that we could get out of this case. The other important thing to consider is the actual power requirements. So CFD can help us understand how changes in the configuration of the drone itself can impact the thrust generated or the drag experienced by the vehicle, as well as its handling qualities. So you might want to investigate what happens if we have something like a 6-rotor aircraft or a 4-rotor aircraft. And we can see the power or the force plot here generated from the rotors. So we can see that we've got a rotor power of around 544 newtons created here. And obviously we can get each of these force plots for all of the different ground effect heights so that we can get a real good understanding of how the different ground effects are impacting our quadcopter. Okay, so that's some of the analysis that we can run. Obviously, I haven't got time to go through this in great detail through every one of these simulations, but we can also provide this project after the webinar so that you can come in and have a more detailed look at what we actually did here. But the other thing I do want to cover briefly, you're obviously wondering, how can I set up this simulation and how can I run this simulation myself? Well, it's very straightforward and quick and easy to set up a simulation like this. The first thing we need to do is import a geometry. And in this circumstance, I'm dragging and dropping a PowerSolid geometry into SimScale to import that. We also support many proprietary formats from all of the major CAD softwares and other intermediary formats as well. For example, we have a plugin for SolidWorks and Onshape, so you can get those CADs directly into SimScale. Once you've imported the geometry, you can then prepare it for simulation by using our inbuilt tool called CAD Mode. This allows you to prepare the geometry for simulation. So one of the things that hasn't been done here yet is we haven't created a MRF zone for this propeller. So I just need to select some of the faces of that propeller and specify some clearance factors so that SimScale can then generate a cylinder that we can use as an MRF zone. Okay, so once we've got that cylinder created, our geometry is ready. We've got the MRF zones and the quadcopter. We then need to do an external flow domain creation so that we can create the flow domain for our air, and we'll omit the actual MRF zones, and that will create the flow volume for us to use. And the final step is to delete the quadcopter geometry itself. So once we've got that flow domain created and we've got just the flow domain and our MRF zones for the quadcopter, we can set up our simulation. So from here we can choose the types of simulation that we want to run. And in this circumstance we're using the subsonic solver. This is an excellent solver for rotating equipment, fans and blowers, etc. So if I select that, it creates the tree structure that we need for our simulation. So then all you need to do is go through and turn each of these red items to a green tick. So we assign the air, for example, to the domain, and then the boundary conditions for this actual simulation. But I'm not going to go through and do everything, every single step of this setup. I'll just set up the pressure inlet, pressure outlet, and then we'd obviously want to assign a wall boundary condition to the drone itself and set up the MRF zones. So we just need to create a rotating zone for each of these rotating cylinders. Then once we've done those steps, we can fire off a new simulation. So that was a out of ground effect simulation that I set up. So all we need to do then is start a new simulation. And this submits a new job to be simulated in the cloud. And we can obviously run as many of these in parallel as we like. So if I wanted to change the CAD geometry or change the setup slightly, so maybe I would want to go to the actual rotating zones here and run a different rotational velocity, I could just change those rotating zone velocities here and then set up another simulation to solve in parallel in the cloud. There's completely no load on my machine, and I'll get an email notification when the simulation is complete. So there we can see it's going to take around 10 minutes to complete, and there's 2 simulations running in the cloud now. Okay, so that's all we need to do to get those simulations set up and running. Let's go back to the slides for a moment to have a look at the results that we would get out of this. So what we actually did here was we ran a case from a research paper, and the research paper had used a traditional CFD tool that's shown here as competitor A, and our results match very well with that traditional CFD tool for the various H/R ratios, the different heights, and the thrust that we get out. The experimental results are shown in red, and they're slightly different. They're also slightly different from the traditional CFD tool, and that's due to the geometry being slightly different. So the simplifications for the simulation that we ran in SimScale were the same as the other tool. So that's probably where the discrepancy comes from. But yeah, in a matter of only maybe 20-minute simulation time, you can get all of these design points out of SimScale. And that can also be automated using the API if you want to run hundreds of simulations, for example. Okay, so that's the CFD side of things. I want to switch slightly now to the structural analysis. And what we've looked at for the structural analysis is a vibration analysis. And the main output that we're going to get out of this is a Campbell diagram, so that we can evaluate the natural frequency modes of the propellers and of the drone. The reason for doing this is so that we can design the control system to optimize the stability of our drone at certain hovering speeds. So obviously hover has a specific RPM of the props associated to it for the power requirements. And we want to make sure that we've got a stable platform for doing surveys, taking photographs, etc. So let's go back to SimScale to have a look at how we've done this. Obviously, SimScale is completely cloud-based, so I'm just in the browser, and I'll switch out now to the dashboard. So this is basically an SPDM system that you get for free with SimScale. You've got unlimited storage for your projects, and you can see all of your account activity here. And we're going to be looking at a drone propeller vibration project that I've got set up here. So in this project, we've analyzed the propeller to see what the natural frequencies are of the propeller itself. So we can see that here. And we've analyzed this at 10,000 RPM. So what we expect to be the hover RPM for these propellers. And we can analyze this to see what the eigenfrequencies are. And we can see the different eigenfrequencies, the different flapping and bending frequencies of the propellers. So this is really important because this informs us what the natural harmonic frequencies are going to be that ideally we're going to want to avoid. We can then take this a step further and run a harmonic analysis. So this takes the natural frequencies that we ran, includes the damping properties of the material, and then for each of those eigenfrequencies we can hone in and look at the stress and displacement that we would expect to get for those different rotational speeds. So the first eigenfrequency and the second eigenfrequency, we can see that we'd definitely be getting some relatively high stresses at the root of the aerofoil. So if we were to dwell at these speeds, it could be a concern that these natural frequencies would develop, and then we would definitely be yielding or fatiguing our propeller material at the root here. So these are really important insights that we can get out of the design. The other thing that we've done here is we've actually taken the entire drone geometry, set each of the propellers rotating to 10,000 RPM, and then we can have a look at the actual global eigenfrequencies for the drone. And this is useful because we can see which ones would be important. So we can see at hover, this third eigenfrequency would be creating a very destabilizing movement. The first eigenfrequency as well rocks the whole drone platform back and forth. So it's important to obviously avoid these eigenfrequencies if we want a stable platform for taking photographs and doing surveys. So after running all of these different simulations, the main output that we can get out of this is a Campbell diagram. So this Campbell diagram allows us to look at the different frequencies. So each of the horizontal lines here represents one of the natural frequencies. And we're looking at this for the propeller, made from a certain material. So in this circumstance, it was a PVC material. And then we can see the operating points on the Campbell diagram. They're the diagonal lines. So the blue is the main operating point. So 1 rotation of the propeller corresponds to 1 Hertz. And then we've got the second and the half operating point. So the main operating point is the main one we want to look at, and wherever that crosses with one of the frequencies, that is potentially going to be a dangerous intersection point. So with this material and this geometry, we would definitely want to avoid 1630 RPM and 6600 RPM. At our expected hover, there is potentially an issue at 10,000 RPM as well. So my recommendation here would be to change the material or to change the design of the propeller slightly to shift these eigenfrequencies so that we don't have an eigenfrequency at our hover. Okay, so that's the results from each of those. So in summary, we've looked at how we can analyze the effect of ground proximity. So with SimScale, we can simulate complex aerodynamics, evaluate drone performance and stability, and design aerodynamically efficient drones. And from the structural point of view, we've looked at how we can generate a Campbell diagram to mitigate for vibration, evaluate the stresses and the durability of those components, and assess the drone's structural integrity. Thanks. Okay, we'd be happy to answer any questions now.
All right, Steve, thanks very much. Yeah, we've had quite a few questions come in on the chat. We only have a few minutes left, so I'm going to pick out a couple, Steve, and have you answer them if that's okay.
Yeah, of course.
Thank you very much. Yeah, so let's have a look. One question came in, so are we using the moving mesh method?
Okay, yeah, it's a good question. So at SimScale, we don't use a moving mesh. We're relying on the mesh refinement zones that we set up in advance and using those to be efficient. Obviously, we got these results in the space of 10 to 20 minutes per simulation. So we were able to get very efficient simulation results without the need for a moving mesh. If you want even faster results, you could, of course, take advantage of the symmetry of a drone like this, and then you could get results out in around about 5 minutes. Thanks.
All right. Thank you, Steve. Excellent. All right, let's have a look. Okay. Does the vibrational simulation, does it provide a mass participation plot?
Yes, so there is various plots that you can get out of the post-processor, and we take the, when we're calculating the eigenfrequencies, we're taking the centrifugal forces into account and also the gyroscopic effects. And you can get the full detailed table out of the post-processor. All
right, let's go for one more. Slightly different area, but it's a question about what browsers are supported. This is all running in your browser.
That's right, yes. So for this demo, I was using a Google Chrome browser. Our officially supported browsers are Google Chrome and Firefox, but generally SimScale works on any of the main browsers. So Safari, for example, also works, but we guarantee that it will work on Chrome and Firefox.
Lovely. All right, Steve, well, thanks very much. Okay, we are running out of time. So what we'll do is we will follow up after the event with answers to the questions we didn't get to. So while I'm continuing to talk, it's your last chance to ask more questions, but we'll capture those and we will follow up. You'll get an email from us. So with that, let's move on to sort of last piece of information that we want to share with you, and that is the next steps. And basically, well, I really hope that you found the webinar valuable. I hope you've enjoyed Steve's excellent demo, looking at the various capabilities applied to drones. You can see we've just really touched the tip of the iceberg there. There's a lot more capability that we haven't been able to jam into this 30-minute session. So hopefully you're keen to have a crack at it yourself, and the way to do that is basically just open up your browser and go to worldwideweb.simscale.com, and you'll see along the top it's pretty clear to see where there's a sign up, but if you just go /sign up in that URL, you'll be able to get started basically free of charge right away. You can also go in and request a one-on-one demo by contacting us directly at sales@simscale.com, and basically you'll hear back typically within 24 hours of business day, and you'll hear back from an application engineer, and if you're really lucky, you'll hear back from Steve as well. So with that, thank you again.
Thank you. Goodbye.